Hello students, welcome once again. Hope all are fine. Till now, we have understood the concept of retaining wall, various stability conditions, and the design of various elements of cantilever retaining wall. In today's lecture, we will see the various applicable stability conditions as well as the design procedure of counterfort retaining wall.
The cantilever retaining wall, as discussed in our previous lecture, is economical up to about 5 to 5.5 meter of retaining wall height. As the height increases, the moments in the stem, heel and toe increases rapidly and thus the wall becomes uneconomical. The deflection of wall also increases rapidly. The counterfort wall are used for such cases. In counterfort retaining wall, the stem and the base. This is the stem and this is the base. In counterfort retaining wall, the stem and the base are tied together by counterfort. This is the counterfort. At suitable interval. This is the center to center distance between the counterfort. Because of the provisions of counterfort, the vertical stem, this is the vertical stem, as well as the heel slab, this is the heel slab, this complete strip is a heel slab, acts as a continuous slab. This is a continuous slab in this direction, the stem is a continuous slab in this direction. Continuous slab in contrast of the cantilever retaining wall. In cantilever retaining wall, this heel slab and this stem slab acts as an cantilever slab. The counterfort acts as a tension member. This counterfort acts as a tension member to support the stem and reduces the bending moment in it. This counterfort reduces the bending moment in this stem. It also provides the support to the heel slab and reduces bending moment in it also. It also reduces the bending moment in the heel slab. Generally, the counterforts are spaced at an interval of 1/3 of the height of the wall. The stability of the retaining wall is maintained by the weight of the earth on the base slab and its self-weight. Counterfort retaining wall are economical for a height over about 6 meter. Now let's discuss some deflection profile of a counterfort retaining wall. As discussed previously, this stem slab acts as a continuous slab about the counterfort. This is the plan view of stem slab. The active soil pressure is acting in this direction as shown in figure. This is the deflection profile of the stem slab as seen in the plan view. At the mid-span between the two counterfort, the tension phase will be away from the backfill, means this is your tension phase. Hence, the reinforcement, main tensile reinforcement will be on the outer phase or away from the backfill between the two counterfort in the stem slab. At support, means at the connection between counterfort and the stem slab, the tension phase will be towards the backfill. These are the tension phase. Hence, the main tensile reinforcement at the junction between the counterfort and stem slab will be towards the backfill. This red line represents the main tensile reinforcement. This is the elevational view or the front view of the base slab, means this base slab. We are looking the counterfort from this face, that's the front face. This is the base slab, these are the two counterforts. This is the deflection profile of the counterfort. Here the base slab is tied at the counterfort, hence deflection will be zero at these points. Due to this backfill weight, the deflection profile will be like this. Here we can see that between the counterfort, the tension phase will be away from the backfill. This is the tension phase. While at the connection between the base slab and counterfort, the tension phase will be towards the backfill. This is the tension phase. Hence, main tensile reinforcement between the two counterfort will be in the bottom layer, while main tensile reinforcement at the junction between base slab and the counterfort will be towards the backfill. This red line represents the main tensile reinforcement.
Now let's see some stability conditions and design procedures of counterfort retaining wall. Stability. Considering a unit length of wall for checking the stability is conservative because the weight of counterfort is more than the weight of the earth of its volume. Hence, we can neglect the weight of counterfort in our stability check. The factor of safety against overturning and sliding should be satisfactory as we have done in our cantilever retaining wall check. The upward soil pressure should not be more than allowable soil bearing pressure and not less than 0. The stem is designed as spanning between the counterfort and loaded with a triangular load from the active soil pressure. While in cantilever retaining wall, we were designing the stem as a cantilever slab. As the loading on the stem is variable, the stem height may be conveniently divided into 2 or 3 parts for the design. At the connection between the stem and counterfort, tension is induced, hence shear force is checked at the face of the support, that is, at the junction between the counterfort and stem slab. Base slab. The inner footing, that is the heel portion, is supported on 3 sides. 2 sides are supported by counterfort and one side is supported by the stem slab. Heel slab is designed as spanning between the counterfort support. Outer footing, that is the toe slab, is designed as an cantilever slab subjected to the upward soil pressure minus self weight of the toe slab. Weight of soil above the toe is usually neglected as it may be removed due to a soil erosion or some other accidental activity. Counterfort. The counterfort supports the stem and base slab. Counterforts are designed as vertical cantilever beam of varying cross section. The connection between stem and counterfort and that between the base slab and counterfort in the form of stirrups shall be provided to transfer the load. Now let's go for our third example. Here we are supposed to design a counterfort retaining wall to retain an earth mass of height 6 meter. Unit weight of soil is given as 16.3 kN per meter cube. Angle of repose is 30 degree. The coefficient of friction between the base slab and soil is 0.6. The allowable bearing pressure of soil is 150 kN per meter square. Here grade of concrete to be used is M20 and the grade of steel to be used is Fe415.
Now let's solve the example. Here step 1 is to find the coefficient of the earth pressure. 5, that is the angle of repose, is 30 degree is a given data. Ka is the active soil coefficient is equals to 1 minus sin phi upon 1 plus sin phi, which comes out to be 1 by 3. While Kp is the passive soil pressure coefficient is equals to 1 by Ka is 3. In step 2, we are supposed to determine the preliminary dimensions of our retaining wall. Our step A, that is 2A, is to find the depth of a foundation. This depth of a foundation can be determined by our classic soil mechanics formula, that is QO, that's the soil bearing capacity divided by unit weight of soil into Ka square. QO, that's the soil bearing capacity, is 150 kN per meter square is a given data. Again gamma is 16.2 kN per meter cube is also given data. Substituting all these values, that is gamma, QO and Ka in this equation, you will get a minimum foundation depth as 1.03. Say we will take as 1 meter. This is the foundation depth. This is the height of the soil to be retained, that is 6 meter. Therefore, overall height of the wall will be equals to the soil retention height, that is this. Soil retention height plus foundation depth, that comes out to be 7 meter. That 6 plus 1 makes it 7 meter. Width of a base, that is 2C step. For an economical design of an counterfort retaining wall, the base width should be between the range of 0.6h to 0.7h. That is, in other way, we can say that the base width should be between the range of 4.2 meters to 4.9 meters. Let us take the base width as 4.5 meter. This is our base width, that is 4.5 meter. Point A to point B, this is 4.5 meter. Then toe width will be equals to 1/3 of B, that comes out to be 1.5 meter. This is a maximum toe width. Therefore, assume toe width as 1.25 meter. Hence, this toe width, this is the toe width. A to C is the toe width is 1.25 meter. Step 2D is the thickness of the base. For economical dimension of base slab, the thickness should be in the range of h by 20 to h by 15. That is, it should be between 0.35 meters to 0.46 meters. Therefore, let's try 400 mm as our base slab thickness. This is the base thickness from capital A to small a. This is 0.4 meter. This is our base slab thickness. Spacing of counterfort. For economical design, the spacing between the counterfort should be determined from the following relation, that is 3.5 into h by gamma whole raised to 0.25, where h stands for the overall height of the retaining wall, gamma is the unit weight of soil. This comes out to be 2.84 meter. Therefore, provide 3 meter as in center to center distance between the counterfort. This means that we are having a distance between these two counterfort as 3 meter and these two counterfort as 3 meter and so on. Means the distance between the counterfort to counterfort is 3 meter. Now, thickness of stem slab. First of all, height of the stem will be overall height of the retaining wall minus base slab thickness. Overall height of the retaining wall is 7 meter, out of which 0.4 meter is to be subtracted. You will get height of stem slab as 6 meter plus 0.6 meter. Its h is 7 minus 0.4 is 6.6 meter. Pressure at stem base. Pressure at CD point is equals to Ka gamma h. Ka is 1/3, gamma is 16.2 and h is 6.6. Sorry, I have written it 5.6. It's 6.6. This is the height of stem slab. Therefore, pressure at stem slab will be 1/3 gamma h. That comes out to be 35.64 kilonewton per meter square. This 35.64 kilonewton per meter square is the pressure intensity at CD point. This pressure, that is 35.64 kilonewton per meter square, is the pressure intensity acting in this direction, perpendicular to the stem plane. That will cause a deflection in this direction. The bending moment at this point, it's the connection between the counterfort and the stem slab, will be equals to WL square by 12, where L is the distance between the two counterfort. W is 35.64 pressure intensity. This is moment intensity at support, and at mid span, that's mid distance between the two counterfold, is WL square by 16. We are considering this slab to be continuous over the counterfold. This formula of WL square by 12 and WL square by 16 is given in table number 12, page number 36 of IS 456-2000. We will get maximum bending moment at support since we are having minimum value of denominator in the formula of bending moment at support. Therefore, substituting all values in this formula, that's WL square by 12. W is the pressure intensity at stem base, L is the center to center distance between the counterfold, 12 is the constant. We will get bending moment, this is negative bending moment, as 26.73 kN meter. Factored moment will be equals to 40.1 kN meter. For Fe415, we are having mu is equals to 0.138 FCK BD square. Mu is 40.1 kN meter, FCK is 20, B is 1000 mm or 1 meter length of wall, D is unknown. Substituting all these value, you will get D as 120.54 mm. Taking into account the shear criteria which we are going to check afterward, we will provide a larger depth, somewhere about 2 times than that what we have obtained in our flexural criteria. Therefore, we will try a depth of 250 mm at stem base, which will get reduced to 160 mm at top. We will assume clear cover as 40 mm. We will assume main tensile reinforcement as 10 mm dia. Therefore, effective depth at stem base will be equals to overall depth minus clear cover minus main reinforcement diameter divided by 2. That comes out to be 205 mm. This depth will be used further in our design procedure. First of all, we are supposed to go for a stability check. First, we will consider the horizontal load only. Therefore, the active soil pressure, that's this pressure, the soil due to backfill. We are having a base pressure of soil pressure diagram as Ka gamma H. Ka is 1/3, gamma is 16.2 and H is 7 meters, just total height of retaining wall. This area of this triangle will be the total active pressure acting in this direction. Therefore, this will be 1/2 height into base. 1/2 height is 7 meter into base is 1/3 16.2 into 7. Therefore, 1/2, this is the base and this is the height. That comes out to be 132.3 kilonewton. This is the point A where the retaining wall is supposed to get pivoted at the time of overturning. The CG point of this triangle is at a distance of h by 3 from base. From base, we are having this CG point at a distance of h by 3. The distance from point A is h by 3, that is 7 by 3 is 2.33. Multiplication of these 2 points gives the moment about point A. This is the moment about point A. The force is acting like this. This moment will be in anti-clockwise direction. The value of this anti-clockwise direction, also known as moment for overturning, is 308.70 kilonewton meter. Therefore, we can say that the sliding force PAH will be equals to 132.20 kilonewton and overturning moment MO is 308.70 kilonewton meter. Now, let's tabulate the gravity load acting on the retaining wall. First of all, we will consider the backfill. This backfill is for a distance of 3 meter for a height of 6 plus 0.6, 6.6 meter, and the density of this backfill is 16.2 kilonewton per meter cube. Therefore, the weight of backfill will be equals to 3 into 6.6 into density of soil comes out to be 320.76 kilonewton. Its CG distance will be equals to 1.25 plus 0.25 plus 3 by 2. 1.25 plus 0.25 plus 3 by 2. This comes out to be 3 meter. Multiplication of these two values, 320.76 into 3 comes out to be 962.28 kilonewton meter. Now the rectangle portion of our stem slab. This width is 0.16 meter. Rectangle portion of our stem slab is 0.16 into 6.6 into density of concrete is 25, comes out to be 26.40 kilonewton. Therefore, distance from point A of this rectangle portion will be equals to 1.25 plus 0.09, that's a triangle portion base, plus 0.16 divided by 2 comes out to be 1.42 meter. Multiplication of these two values give the moment about point A. This moment will act in a clockwise direction. This above moment will also act in a clockwise direction. Triangle portion of this stem slab. This stem slab is sloped away from the backfill. Base of triangle portion is 0.09. Height of triangle portion is 6.6 meter. Therefore, it's 1 half 0.09 into 6.6 into 25 is the density of concrete, comes out to be 7.44 kilonewton. Distance of CG will be equals to 1.25 plus 2/3 of 0.09, that is 1.31 meter. Multiplication of these two values comes out to be 19.73 kilonewton meter, which is a clockwise moment. Base slab width is 4.5 meter, its thickness is 0.4 meter, concrete density is 25 kilonewton per meter cube. The multiplication of these values comes out to be 45 kilonewton. Its CG distance will be 4.5 meter divided by 2. Therefore, the multiplication of these two values give the moment about point A, that is 101.25 kilonewton meter, which acts in a clockwise direction. Summation of all these load, that's W1, W2, W3 and W4, comes out to be 399.60 kilonewton, and summation of all these moments, which is also known as restoring or resisting moment, will be equals to 1110.75 kilonewton meter. I have summarized these loads as total downward load, that is the load acting towards gravity at sigma W is 399.60 kilonewton, and total restoring or resisting moment is 1110.75 kilonewton meter. Now let x be the distance of vertical forces from point A. Let this x be the distance of all vertical forces, this is sigma W, from point A. Therefore, for an equilibrium at point A, sigma m should be equals to 0. That means sigma W into x should be equals to net moment acting at point A. Therefore, x will be equals to mr minus mo. Mr is a clockwise moment minus anti-clockwise moment divided by summation of all vertical forces. This comes out to be 2.01 meter. Eccentricity, which is measured from the center of base slab, which will be equals to b by 2 minus x. E will be equals to b by 2 minus x. b by 2 is 2.25 meter, that is 4.5 divided by 2, and x, what we have derived, is 2.01 meter. This comes out to be 0.14 meter. Now we will go for 3 checks which we have carried out in our cantilever retaining wall design also. Our check number 1 is for soil bearing pressure check. That is P max is equals to sigma W by B 1 plus 6e by b. This is an equation which you might have studied in your direct and bending theory. Here sigma w is the summation of all vertical forces, b is the base width, e is the eccentricity. Substituting these values, you will get an answer as 117.22 kilonewton meter, which is smaller than your SBC, that is 150 kilonewton per meter square. This is your given data. Therefore, we are safe as far as maximum pressure is concerned. For minimum pressure, we will use the formula sigma W by B, 1 minus 6E by B. This comes out to be 60.34 kilonewton per meter square. These two pressure values are shown here. The maximum pressure at point A is 117, that is this, 117.22 kilonewton per meter square is this, and minimum pressure, that is 60.34 kilonewton per meter square is this. This 60.34 kilonewton per meter square is greater than 0, hence there is no tension condition at heel slab end. We are having no tension condition at this point, that's heel slab end. Hence we are safe as far as minimum pressure or tension is concerned. This is our check number 2. It's a factor of safety against overturning. Our overturning moment MO is 308.70 kilonewton. Our stabilizing moment MR is 1110.75 kilonewton meter is this value. Again, factor of safety against overturning is MR upon MO comes out to be 3.60, which is greater than 1.55. This 1.55 is the limiting condition given in clause number 20.1, page number 33 of IS 456-2000. Since our factor of safety is greater than, that is 3.6 is greater than 1.55, we are safe against overturning. Check number 3. Factor of safety against sliding. We are having a sliding force of 132.3 kilonewton. We are having a restoring force, that is a frictional force, is equals to mu into sigma W. Mu is 0.6 is your given value into sigma W. Sigma W is the summation of all vertical force, that is 399.60 comes out to be 239.76 kilonewton. Factor of safety against sliding is restoring force divided by sliding force, that is 239.76 divided by 132.30 comes out to be 1.81, which is greater than 1.55. 1.55 is the limiting condition given in clause number 20.2, page number 33 of IS 456-2000. Since our factor is greater than the limiting factor, we are safe against sliding.
This ends our lecture. In next lecture, we will design stem slab, base slab, toe slab and counterfold. Till then, thank you.